So part A, we have 7 milliliters of base added. That means that V2, in terms of the dilution, our final volume is in the Erlenmeyer flask is going to be 7 milliliters from the base plus 20 milliliters from the acid, or 27.0 milliliters total. And when we do our mathematical modeling here, the first thing I want to do is consider the dilution effect. And so I'll calculate these up top. For the HBr being diluted, our final molarity will be M1V1 over V2. And again, this is just the dilution effect. The initial molarity was 0.2. The initial volume was 20, and our final volume is 27. So if we run this through a calculator, we're going to have 0.2 times 20 divided by 27, and as we've combined these solutions, the molarity of the acid will drop to 0.1481. I'm going to keep like one extra sig fig because all of the numbers we were originally given had 3. Keep one extra sig fig to round to prevent cumulative rounding errors. So that was the HBr. The calcium hydroxide is going to have an M2 of, let's see, M1V1 over V2. And that's going to be M1 was 0.2 molar, V1 was 7 mils, and V2 was 27 mils. So by the time we run all of that through a calculator, we'll have the concentration here for the base. Let's see, I'm running out of room to write this, so I'll squeeze it in over here on the left. That'll be 0.05185 molar. Now I'm going to take this one step further, and from the calcium hydroxide concentration, calculate what the hydroxide ion concentration is, because for every 1 calcium hydroxide, we're going to get 2 hydroxide ions. Excuse me. So we will end up with 2 times 0.05185. Which is going to give us 0.1037 molar for the hydroxide ion concentration. Now, since HBr is monoprotic, its H plus ion concentration will be equal to the HBr concentration. Now, as this neutralization reaction is taking place, we're going to have H plus from the HBr reacting with OH minus from the CaOH2, and that's going to give us water. Now we're going to set up something that's very similar to an ICE chart, but I'm going to make this an ICF chart. F stands for final. This is not an equilibrium reaction. This is simply a table to help us keep track of the molarity of all of the chemicals that are reacting. So initially for H+, we have a diluted value of 0.1481. Initially for hydroxide ion, we have a diluted value of 0.1037, and water doesn't affect the pH, so I'm just going to squiggle it out so that I don't waste time attempting to put a number on it. Now, when I look at the H plus and the OH minus, I've got more H plus, so that means it's my excess reagent. My limiting reagent is the hydroxide. So all of that hydroxide will react, so the change will be minus 0.1037 in the hydroxide, and that's also how much of the H plus will react, because that is the excess reagent. The excess reagent will react with the limiting reagent until the limiting reagent is entirely used up. So the final value will be 0 for the hydroxide ion, and for the hydrogen ion, it will be 0.1481 minus 0.1037. 37, and wow, I just totally typed that wrong in my calculator. Let's try again. I got a number in the thousands instead of a number smaller than 1, so I know that wasn't right. Here we go. This number looks a lot better. It is 0.0444. So when this neutralization reaction has finished, the concentration of H plus is 0.0444. So that means that the pH of the solution will be minus the log of 0.0444, which will be 1.35261 and a bunch of other digits. Let's see, I've kind of lost track of my numbers here. We had 3 sig figs originally in our molarity, so this should round to 3 decimal places, so 1.353 for the pH after 7 mils of base have been added. All right, let's try again now with a different concentration, or I'm sorry, a different volume of base added, 9.6. Our V2 for our dilution calculation will be equal to 20 mils of the acid plus 9.6 mils of the base, so that will be 29.6 mils total for our V2. And if we're going to calculate the dilution of HBr, M2 will be equal to M1 V1 over V2. M1 for the acid is 0.2. V1 was 20. V2 was 29.6. So if we run that through a calculator, we get 0.135. Yeah, probably should keep one more sig fig. So for HBr, we have a concentration of 0.1351 molar. For the calcium hydroxide, the molarity of the calcium hydroxide after it's diluted will be 0.2 multiplied by 9.6 and all divided by 29.6. And that will be equal to 0.06486. And then we're going to want to multiply that by 2 to get the hydroxide ion concentration, since we get 2 hydroxides for every 1 calcium hydroxide. So that will give us 0.1297 molar for the hydroxide ion concentration. Now, if we look at our net ionic equation for the acid-base neutralization reaction, H plus plus OH minus yields H2O. Let's look at our change in our final values. We'll squiggle out water since that won't affect the pH. Initially, for the acid, we have 0.1351 molar. For the base, we have 0.1297 molar. Still, the acid is present in excess, and the hydroxides are going to be our limiting reactant because it's smaller, so that will be a minus 0.1297 as it all gets eaten up. And so we'll subtract 0.1297 from the acid, so that negative plus 0.1351. All right, so that's going to leave us 0.0054 molar H plus ion when all of that base has been added. So pH will be minus the log of 0.0054 or 2.270 to keep those 3 decimal places. Part C is where we get to take a breather because we discovered that 10 mils of base added is the equivalence point, and since the salt that's being produced is, CaBr2, which is a neutral salt, the pH of a neutral salt is simply 7, no calculation needed. All right, one more part. At 15 mils of base added, we are past the equivalence point. So this means that all acid has been converted to salt. So there's no acid present, and we are 5 milliliters past the equivalence point, and so that means that we have excess unreacted base. All right, so when we set up our ICF table, we should end up with a value for hydroxide ion, and then from that we can calculate our POH and then pH. So let's take a look at the dilution effect here. We started with 20 mils of acid, and we've added 15 mils of base, which gives us 35 mils of solution total for our V2. For the HBr, we're going to have an M2 of, let's see, M1 is 0.2 molar and V1 is 20 mils. And we're going to divide that by our V2 of 35 mils. So our HBr gets diluted out to 0.1143 molar for that HBr. For our calcium hydroxide, M2 will be M1, which was 0.2, times the volume added, which was 15, divided by our final volume, which was 35. So we'll have 0.2 times 15 divided by 35, and that will equal 0.08571. But that's for calcium hydroxide. To get hydroxide, we'll have to double that. So multiply times 2, and I get 0.1714 molar for the molarity of the hydroxide ion. Notice this is bigger than our HBr value, which is what we were predicting since we are past the equivalence point. So our net ionic equation for the acid-base neutralization is H plus OH minus yields H2O. If we set up our ICF table, initially for the acid we have 0.1143 molar. Initially for the base we have 0.1714 molar. We'll squiggle out water. The acid now is smaller, making it our limiting reagent. So the change will be 0.1143 minus 0.1143. So that gives us 0 for the acid and 0.0571 for the base. Now we can't just take minus log, or well we will, but that's not going to give us pH. It'll give us POH because this value right here corresponds to hydroxide ion. So POH is minus log of 0.0571. So I'll take log and change the sign, and we get a POH is equal to 1.243. So the pH would be 14 minus 1.243, which will be 12.757. So after 15 mils of base have been added, we are at a pH of 12.757. Well, those titration calculations where you're stopping along the way and trying to figure out what the pH and all of those is, those get tedious and repetitive. So it's easy to make a mistake somewhere in there. Just be careful with your math. So our objectives were to take a look at these titration curves. We'll do the comparing and contrasting in the next video, but we've at least seen what a titration curve looks like, and we saw how to calculate the pH values along the way on these titration curves.